Hi, and welcome to another old steam-powered machine shop. Just catching up on my reading here. Rogers Erecting and Operating Manual, 1914. I've just spent probably 50, 75 hours working on this line shaft system to get the planer hooked up to the steam engine. And the thought occurred to me that, at the beginning of the last century, when machining technology and machinery just exploded, the manufacturers could not make the stuff fast enough. The steam engine companies couldn't make steam engines fast enough. That's why there was hundreds and hundreds of different makes in the United States. And this was all fueled by the railroads and the steel industry and the oil industry, and small shops, job shops, small manufacturing. So the Whitcomb company here, by 1899, had made over 2,600 planers. And they're just one little, I wouldn't say they were little, but they were just one company. There was hundreds of companies making planers back then, if you want to look at just planers. So these things went all over the country and Canada, and they went into shops that were overloaded with work. That's why they're buying it in the first place. So who sets these things up? Who moves them in, lines them up, figures out where the belt has to go in order to get to the machine, the best way to hook it up, figures out the speeds, the pulley sizes, where the shafts have to go, lines up the shaft, makes the belt, and the larger shapers. This is a 24 by 24 by 8 feet. This is the upper end of what they called small planers. They were pretty much ready to go. But anything bigger than this came from the factory, sort of roughed out, and the installer had to line up the bed, jack it up and level it, and then scrape the ways to get things to move right and be level and parallel. And then I read in one manual where they even had to machine the back side of the rack that ran the whole length of the table in order to get proper engagement. So who did all this? Now, the shop is running up to capacity. The shop superintendent is not going to have time to do all this. It's certainly not the shop owner. So there was born a whole new occupation called millwrighting. And these guys had to know everything. They had to know how the building trades. They had to know how to build buildings. They had to know how to build floors. They had to know the machines inside and out, how to put them together, how to take them apart, how to fix them, how to line them up, and line up the pulleys, the whole 9 yards. I mean, they had to know everything. And when something wasn't right, they were the guy that had to be called. So, you know, these guys just had to get experience from wherever they could to be a proper millwright. So, you know, it was an amazing time in industry in the United States. I found in my belt pile what appears to be brand new old stock. It's 1.5 inch 2-ply, which is kind of unusual for 1.5 inch belt. Makes me think that it might have been manufactured for planer belt. You can see right on the edge here it says this side 2 pulley. So I'm going to cut a piece and put it on for the drive side. It's a brand spanking new belt. It'll probably stretch quite a lot. It's got to be crossed because this is the drive belt. They also run another reason they run the drive belt cross is it gives it more wrap on the pulleys. Oh yeah. Okay, here's the mark right here. Handy dandy belt cutting device. Makes a nice edge. Gonna put clipper lacing in this belt because it's thicker than the single ply belts that I use elsewhere in the shop. This is 5/16 thick, being 2-ply. I'm going to use the UC or U4C clipper lacing, which is made for 11/32 to 1/4 inch. And I like the U series. They call it a Unibar because it's got this extra wire spot welded in here and it holds things together. So we need that much. Okay, I don't think this is new old stock, but it's seen very little use. Put the little tag wire to the outside. Right there, it's stamped all over it. This side, the pulley. Come on. Oops. Probably that way. Another thing you got to do is when you crimp these in there, it tends to swell the last little bit of the belt out, so to avoid it having a bump there on the side, I'll grind just a little off of there. Needs foot oil. This is the mechanism that shifts the belts to change direction of travel of the table. And on the return stroke, when the table is running in this direction, this dog here, which is adjustable anywhere along the table, it is adjusted to hit this and shift the belt. But it's had a hard life. It's a casting. Someone's tried to repair it by arc welding it, and it's been worn a lot and built up, and I'm thinking about making a new one out of a piece of steel stock, one piece, or maybe a heavy piece of angle. I don't know, but anyway, this is pretty important, so it's got to be working right. This is 18 feet of 1 7/16 wrought iron line shaft that we pulled out of West End Machine Shop in Wilmington when we got the planer, and it's in pretty good shape, but it's really caked up with belt resin and grease, which requires 2 different kinds of solvents to get it off, and it's a lot of work to clean it up. one of the things I got to do before I get much further is to figure out the pulley sizes in order to run this at a proper speed. I'd like to run it a little faster than what it was set up down in Delaware. So first thing you got to know is per revolution of the drive pulley here, how far does this table move? Now I got a dial indicator set up over here, and I got a mark on the pulley, and I'm going to roll it over one turn and see what we get. I've got the backlash out of the table in this direction. Right there. Indicator shows 1 inch, 0.145, actually 7. 1 inch, 0.147 per turn of the pulley, inches in that direction. Okay, you might be interested in how I figured this all out. Per revolution of the planer shaft, the lower shaft, you get 1.145 inches of table travel. And the other thing I know is that the main shaft that's driven by the steam engine in my other part of the shop is 260 RPM. So eventually that's going to get to the planer through these pulley ratios, because these are the pulleys that I had in stock that I could use, and it seemed like the best setup I could come up with. I got a 15 inch on the main shaft, a 14 inch on the number 2 shaft that I'm going to put up, and then that drives to the counter shaft over the top of the planer by an 18 inch pulley to an 11 inch pulley on the counter shaft, and then on the planer itself is a 13 inch pulley on top and an 18 inch pulley on the bottom main shaft of the planer. That's the 3 pulleys that the belt shifts across. Those are all 18 inch in diameter. So if you multiply these out, you get an overall ratio of 1.26 to 1 against my main shaft in the old shop. And that shaft runs at 260 RPM. So you multiply that by that ratio and you get 327 RPM at the planer shaft. Okay, 327 RPMs times the 1.145 inches per revolution that I just measured with the dial indicator equals 375 inches per minute of table travel. Or you divide that by 12, you get 31.26 feet per minute. Well, that doesn't sound like much surface speed for a cutting tool. I mean, you know, a high-speed steel on a lathe, you figure you want it up around 90, 100, maybe even more than that on mild steel. But if you, in order to kind of illustrate to myself anyway, I took a 4-foot rule and laid it out here, and with my stopwatch I ran along it, and at this speed it's going 31.3 feet in 60 seconds. So how long will it take to go 4 feet? Well, you set it up an equation and you solve it, and it comes out to 7.66 seconds. So that tool will cover 4 feet in 7.667 seconds. And the return with the 20-inch pulley up there, the straight belt, figured into this ratio up here. It returns at 48 feet per minute, or it'll cover the 4 feet in 5 seconds. So at those speeds, if you were planing off something that was 4 feet long, it would cover the 4 feet in the cutting direction in 7.66 seconds, and then 5 seconds to return. And you know, you figure you got 1,000 pounds or more of this table, plus the weight of your workpiece, which could be a couple hundred pounds maybe, and you're having to stop and reverse that, going back and forth. That 31 feet per minute seems like a reasonable limit. I've read in old shop manuals where they were approaching 40 feet per minute with modern planers back in the 30s. But in this shop, I think I'm going to try that 30 feet per minute and see how it goes. Well, I go to grab a pulley off the pile that I was really counting on using. Got it cleaned up. Found this. Another setback. Gotta fix it. Question is, do I want to arc it up with nickel rod or braze it? Arc welding it would be quick and easy. A brazing would be doing it the right way. I got the 18-inch pulley on the balancing rig, and you can see it's way out. Of course, my repair didn't help things any, but it's dressed down and you wouldn't think it would make that much difference. It's kind of amazing to me that these pulleys could be that far out and there doesn't seem to be any attempt by the manufacturer to balance most of them. Oh, we're getting close. I got 4 of these big old nuts taped in there, and it could stand just a little bit more, but I'm gonna take them out and weigh them and see what I got. Right about at 12 ounces. So I'm gonna shoot for 13. There's about 13. Oh, we'll put it in here and heat it up. The 14-inch pulley's got to get bored to 1 15/16. That's not going to leave a whole lot of material here, but it's the only pulley I got, and I think it'll work. This is a pretty cheap pulley. It's very thin, and it's as cast here. I don't think there's enough material here to completely machine this outside, but it runs fairly true. So I'm going to bore this out and then clean this surface up and balance it.
spots in on the edge of that. And the cast iron is fast.
Finished bore. I just beveled this a little bit on both sides. Took a little off here to kind of even it up and smooth the edges off. In case the belt ever comes off, it doesn't tear the belt up. Now we'll see how it balances out.
not so good. Well, that one didn't take as much. Two notes. Like about 4 ounces. The counter shaft drive is set up. The tight and loose pulleys are lined up and the belt's made up. I had determined where the shaft had to go in order to get around the ceiling joist here, and I would have been fine, except I changed my mind and I put an 18-inch pulley on the shaft instead of the 14, and so I had to notch it out a little bit on the bottom, and I got to notch it just a little bit more, but it'll be okay. Up on top, I put a ball bearing pillow block bearing because I didn't have enough room to put a regular hanger in there. So the timbers are lagged with 3 lag screws on 3 ceiling joists on that, and the timber up here on this end of the counter shaft runs 1 joist left and 1 joist right, so it's actually lag screwed to 3 ceiling joists to spread the load out. And the shaft is level, and you can see how far off the ceiling is. Well, if you look through the opening here, you can see the main shaft out through on the back part ceiling. And 1 hanger up close to the wall, and then divided the space equally on the second and third. That pulley is just about where it's supposed to go right now, and the belt will drive across to the other shaft. I've got to move a few things around on that shaft to get room for it. It's about a 20-foot span. Well, that's about it for this time. Sorry I didn't get any video or even any still shots of putting up the line shaft. I had about 6 or 8 guys over Friday night, and they just grabbed it and hoisted it up, hooked up the bearings, and it was done. And nobody thought to take any any photos of it or anything. So to you, it just sort of appeared there, but it was considerable work. Thanks again for taking time to leave a comment or a story about steam power, and I appreciate it. So until next time, we'll see you.